All right, so I'm going to do a problem that uses a bomb calorimeter. And basically what a bomb calorimeter is a container, an enclosed container filled with water that has another container inside of it where you burn whatever thing that you are interested in, whatever fuel that you're interested in. It could be food. And you take the temperature of the water outside of the calorimeter. Sorry, the water of the calorimeter. This is the water of the calorimeter. Okay. So the thing inside of here is our system. Okay, and usually the thing inside of here is our system. And most of these things that you use a bomb calorimeter for are exothermic reactions. So you would expect heat to be going out into the calorimeter and to raise the temperature of the calorimeter. Okay, and so this problem is asking you to calculate the enthalpy of reaction, so the change in enthalpy of this reaction here, where you're burning liquid benzene. And whenever you combust something, you're combining it with oxygen. So that's just a very general definition of a combustion reaction. Okay? And when the fuel contains carbon, you're giving off carbon dioxide and water. And that creates a gas in this chamber. Okay? So you might be saying to yourself, all right, so delta H, we need to calculate delta H. But when I do calorimetry, I get Q, not delta H. And when I do calorimetry, I assume that Q is equal to delta H. And under what conditions is that true? That's true under constant pressure conditions. Well, is this a constant pressure condition here? You are burning this fuel here and you're giving off a gas. You're giving off carbon dioxide and water. All right? But here's the rub. So it looks like the pressure is increasing, right? Because you're increasing the number of moles of gas, and therefore you are exerting pressure on the walls of this insert here, this container where the reaction system is. But consider also that you've got oxygen gas. So you're using up, for every time this reaction occurs, you're also using up some gas. And if you look at the stoichiometry, you're using up 15 moles of oxygen to give off 12 moles of carbon dioxide and 6 moles of water in arguably a liquid form. That's what this says. However, depending on the temperature, it could also be vaporized. So in this equation, as it's written, we're actually decreasing the number of moles of gas produced by a little bit, okay? In another scenario where the water is actually given off as vapor, we would be increasing the number of moles of gas produced by a little bit. In either scenario, it is not a constant pressure situation. However, in a bomb calorimeter, usually the change in enthalpy due to that pressure change is quite small. It's quite a small term. It's like in the hundredths or the thousandths place. And when it's not that small, it's usually factored into the calorimeter constant here. So I went through all that because I want you to be comfortable with the idea that you can actually use a bomb calorimeter to estimate the change in enthalpy, even though it's not a perfectly constant pressure situation. Okay? So we are tasked with finding out the delta H of reaction. Okay? That's a very specific term, the delta H of reaction. What does that mean? Well, it means that we want to find out the delta H of this thermochemical equation, the equation that says exactly 2 moles of benzene are added to exactly 15 moles of oxygen to give off exactly 12 moles of carbon dioxide and 6 moles of water. For that equation with those stoichiometric coefficients, what is delta H? So we know that delta H can be greater or smaller with greater and smaller amounts of things. And when you report the delta H of reaction, what you're reporting is the delta H for that specific stoichiometry. So it's important that you know how much of the stuff that you have so that you can calculate that. All right, let's get started. What are we being asked to do? We're being asked to calculate an energy term, well, a change in energy term, right? And delta H is, in this situation, pretty much equal to Q. So Q is heat. So what equation do we have that equates, that relates heat to a change in temperature? I'm going to come back to that question over and over and over again so that you see how, if you think about it in this way, you can figure out what to do rather than just memorizing a whole bunch of seemingly unrelated equations. What equation do we have that relates heat to temperature? Q equals C delta T. We got heat on this side, we got delta T on that side. And we can manipulate that in several different ways to give us the details that we're looking for, but that is the big idea. That is our equation that relates heat to temperature. We have C, it's given to us here. And we actually also have delta T in this situation. So at first glance, this is a pretty easy equation to solve. We are going to take that C, 551 joules per degree Celsius, and we are going to multiply it by the change in temperature. Okay, we'll cross out our temperature terms to convince ourselves that we'll get joules out of this. And what we get is 47, 40 joules. I'm going to try to follow my sig fig rules. Sometimes I ignore them just because I like to focus on the concepts, but I know that that bugs the heck out of you guys, so I'm trying to be a good model here. It is important to pay attention to sig figs when you're making these physical measurements in lab. When you are trying to think through a problem and think about the underlying concepts and how to work these equations, it's okay to ignore sig figs and then do another problem afterwards where you pay attention to them again. So we've got our Q value here. It's 4740 joules, 4,740 joules. But is that the answer to this question? Is that the heat of reaction? Remember, I told you that the heat of this particular reaction is the heat that is the enthalpy change that is tied to this particular stoichiometry up here. Here, 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 and here. And now we need to figure out, so if the 0.113 grams that we combusted is 2 moles of benzene, then yes, this is the right answer, but it's probably not, right? So we have to figure that out. So how many moles of benzene is 0.113? We know how to figure that out. We use our gram to mole conversion, and I just estimate carbon as 12, so 12 times 6, then plus 6, 1 times 6 for hydrogen. About 78 grams per mole. Divide 0.113 by 78, and what you get is actually a fairly small number of moles of benzene. It's in the millimoles territory there. So this is the amount of heat that you get sorry, this is the amount of, yes, this is the amount of heat that is coming out of a 0.00145 mole sample of benzene. How much heat would come out if it was actually 2 moles, which is what we want for this thermochemical equation, for this heat of reaction, because that's what we're asked for. We just have to do a conversion that says, so we have, here's how I like to think about it. We have a number that says 4740 joules, and that's per, it's not per 1 mole, it's per 0.00145 moles, right? So if we do that calculation, what we get is a per mole value. So let's see here. I'm going to report this in kilojoules. (30-70 kilojoules per 1 mole. So that's how much energy would come out of a reaction if you burned exactly 1 mole of benzene. In our thermochemical equation, we are burning 2 moles of benzene. So I have to do yet another conversion. And I can do all these things at once, but I think it's more conceptual to separate them out. 3270 kilojoules over 1 mole of benzene. But actually we have 2 moles of benzene in our thermochemical equation, so I'm going to multiply it by 2. And I'm going to get a value of 6540 kilojoules. That is the heat of reaction, because that's the amount of kilojoules that are escaping that benzene as it is being combusted. And specifically, that is the number of moles of 2 mole. That's the amount of heat for 2 moles of benzene. So this 6540 equals the heat of reaction. It also approximates to a pretty high degree in this situation the delta H of reaction. Okay, and the little squiggly here would go away if I was very confident that the pressure change term was built into the calorimetric constant. But even if it's not, it's going to be a very, very small contribution. All right, practice more of those on your own. See you later.